Hey guys, welcome back to Henry's Untitled Tutoring, and this is a video on C groups and how it can be used to limit memory consumption of processes on a system. So we'll take a look first at the script that we used in the previous video to initialize our C groups and how that's changed, and then we'll also have a look at an example where we create a process within a group and see what happens when we push our process up to the max in terms of the amount of memory available for that C group. Let's take a look. So the script quickly, there's been a few changes, you can check them out. Of course, I've changed the user now, so I no longer have to be root to do little adjustments to the different files within these C groups themselves. This just makes things a tiny bit easier, and I made some of the naming a bit better on the existing groups. I've also made new groups. These groups have the ability to do the CPU set functions to isolate processes to certain cores, as well as limit memory consumption of my processes. And of course, the same commands are really present here as they were before with the appropriate core values. And then we have down here at the bottom the part that actually declares how much memory each of the memory-based groups will allow for. Simply modifying memory.limit in bytes with either 4, 6, or 8 gigs of RAM in this case. You'll notice that this will actually round off a bit to the nearest block size if we look at one of those files. Let's take a peek at that right now. So over here we have a whole bunch of little happy windows, and we'll start up here with this guy. This is a test box I'll be using separate from my main desktop to illustrate this, just so you can see how it can affect other systems. And this is pretty much just a vanilla install of Ubuntu. So we can have a look first at these little files here. So this file is the memory.fail count. This is an integer value showing how many times there's been an out-of-memory error. That's fairly straightforward, so it increments whenever there's an issue where it's ran out of memory. Next file to look at is, of course, the limit in bytes. So this was assigned a value of 2 billion. It's rounded it off to 1.9 and change on its own. Next one to check out is memory.swappiness. This one is basically, it will start at 60, and it simply dictates to the system how much swap memory do you want to allow processes in this C group to use. And it's usually pretty effective. If you beat up your processes and this is set to 0, they're not going to use any swap space. If you set it to like 20, then they'll put 20% of their consumption into swap, or try to basically. And of course, this guy here is the last one we'll look at quickly. Oops. He is, I can copy please. There we go. He is the current usage in bytes. And if you note, right now there's about 75. That's been divided twice by 1024 and is represented down here in this output. And then the fail count is also down here in this output. This is a loop running, just catting these files and making things a little pretty in the output, so it's easy to see what's going on. And then there's a little loop going on down here that's looking at the current process list. It's trying to find any processes that match Firefox, and it's showing us the total resident memory and shared memory consumed by the Firefox process. So you will see that this will differ here from this value, because this is only going to show us the actual resident memory and the shared memory that Firefox may use. Virtual memory isn't touched really, or isn't factored in at all to this, so that's okay. And of course we have HTOPs, we can see what's going on with our different cores, overall memory consumption, and status on our processes. So let's start off here, we'll run Firefox. We're assigning it, of course, to CPU group 23 and or CPU set 23 and 2 gigs of RAM. And you can see here it's loaded up its previous tabs from when I was last messing with this. And so if I start to cycle through all these tabs, they'll all begin to load, and we should see this consumption begin to jump up. Before I do that, I'm going to run a separate command over here to run a version of LibreOffice on the other CPUs, 0 and 1, in a 4 gigabyte C group instead, so we can sort of have that going as well and see if it gets impacted at all by what we do with the Firefox process. So let's start. We're just going to go ahead and go through all these little tabs. This might lag out here and there just because it's a remote access session to a separate machine. As you can see, as I go through these, the usage is rising, which is precisely what we want to observe. Now, the process status here, or state code rather, is set to S typically, or it may also show R, which basically means S is it's an interruptible sleep condition, and R means it's running actively and doing something. So these are what you would usually see for most cases with your processes. You may see a Z for a zombie process that isn't going away after it's been killed. And what we are looking out for today is going to be a D, which will appear red because that's not something you want to usually see on a system process list. The D indicates a process that is an uninterruptible sleep state. Basically, some kind of I/O condition is taking place to block it from working as expected, and it's waiting for the I/O issue to clear before it can do anything else. So let's just keep going here. We're just going to fire on through this guy until we get to the end, and this should really start to use some RAM. As we can see, the CPUs are being pinned for 3 and 4, which is great. It's not touching our our CPUs for the LibreOffice instance, so this is fine. This won't lag. Everything is good. And we can do other things like open like a dialogue, I don't know. Look at like the page style dialogue, for instance. That's all fine. Hooray. So things are good there. We'll keep going, keep loading stuff. And our goal is to get up to the limitation, which we should reach once we hit approximately 1900 megs of consumption. Then you're going to notice this fail counter will increment, and we might see some errors pop up in here should the system decide to kill off any of the child processes related to Firefox. You'll note we began with like I think 4 children, and now there is a couple more. So the more tabs we open, the more things we do, the more likely Firefox is to spawn additional processes, basically. So let's keep going here. We'll really get this thing going. And we're closing in there nicely. Less than 100 megs to go. This should do it. And there we go. We now see the failure count is incrementing, indicating that we've ran out of memory and that the system is trying to adjust and sort of recover things for us. Now, there's been no error messages popping up in here yet, which means we haven't killed anything off. So that's happy. Let's see if we can make that happen. Our goal is to get this thing consuming enough resources that we start to see processes going into an I/O wait state, which is just what we want to have happen. Yes, that one wasn't going to load. That's fine. Oh boy. Alright, so here she goes. Those numbers are climbing, and I've stopped being able to receive responses. Oh, no, it's still trying. As that is happening, this should still be good. Do some lovely copy and paste, and you can see it's still pretty responsive over there. This guy is upset, and oh, we're starting to see I/O wait condition being hit. There we go. So this is just going to climb a whole bunch now because of this condition, and not much will happen unless it can recover. Now, sometimes it will recover on its own from this state. It may kill a few things, it may get upset, but yeah, so we'll watch here in this little console. Oops. Oop. Get that guy back over here so we can see him. We'll watch this guy. We'll see if there's errors. So we may see some things pop up here if we can really tick it off. But it looks like it's okay right now. Oh, it's recovering, it seems, without killing anything yet. If it does start to actually really kill stuff, then it will definitely have some little messages here for us. And we may see instances where tabs have crashed, which is sort of what I'm trying to go for here. Do its magic. And as it's doing its magic, testing this guy out to see if we're still okay. And I think we will be. As you can see, he's pretty responsive. He's going nuts there. No troubles. Copy entire blocks and just start making words. And hey, at least we're doing something to the poor CPU. But it's, I guess LibreOffice is not multi-threaded. Oh, who knew? Alright, so what's happening here? Anything? No, she's still kind of dead. So what would happen if you're actually using this and you're using your memory limitation functions here of the C group, and you've had a process that's done this, and you're like, oh man, what do I do now? My poor browser's dead. I can't use it. Well, this is where you can just come in here and you can happily pick a child. Let's say you don't like this one. It's using 11, 12% CPU and a bunch of RAM. Just kill it. Off she goes. And bam, a whole bunch of errors pop up because we killed something. So this is probably a couple tabs just died, and of course now it's responsive once again. So if we go back through, we can see, oh yeah, there's one. Any more? That's the one that died, I guess. Pretty impressive actually. We only killed one tab. Not bad. Oh. So by going back through our list of tabs again, we've recreated the issue. That's very nice. I appreciate that. So let's see, will it do anything of its own accord and kill anything off? Sometimes it does. In this case, it doesn't seem to be doing so. So, we'll just recover this. Kill that guy. There we go. Hooray! Oh, that one crashed. That's nice. Down to 1750 or so megs consumed, and we're happy again. The browser is once again useful. We can go and click on things and go and do stuff. And maybe we'll let ourselves to go and close a few tabs down and, oops, I want to save things, thank you. And try and make our browser happier in general. Come on, clear up that usage. That's going down slowly. That's not bad. Yeah, this is more or less how C groups can work when you introduce memory limits, and how you can sort of protect other parts of your system from being bogged down by applications that may consume a lot of resources. A good example of where you may find use for this is if you have a system where you intend to run like some kind of local virtualization with VirtualBox. Let's say you have a Linux machine, you need to run a Windows host within that machine. This would allow you to run the Windows host, for instance, and then protect that in its own little group. Let's say you gave your Windows host like 2 gigs of RAM, you could put it inside a container that has, a little bit more, maybe 2.5 or 3. That way it's going to be fine. And then you can you can go and maybe, let's say you have a web browser you want to use, or some other applications you want to use that would be maybe very heavy potentially on their consumption of RAM. You can put them in their own little group for say 4 or 6 gigs or what have you, depending on how much space you have, how much RAM you have on your system, and how much you want to limit things. And this can sort of isolate stuff to different containers for, I guess, actual consumption of memory. It doesn't actually isolate the RAM like we're doing with the CPU isolation, but it does, if used properly, protect the overall system from running out of memory, because then you still have control. Your X session will still be, functional and actually, responding to commands. You have the ability, should you encounter a situation where one of your applications consumes all the memory in one of these groups, to go on and just fix that application by, as we saw here, maybe killing off some children, or if you really have to, killing the whole application. And you don't have to like pray you get to it in time, and are able to say, go back to your non GUI TTY and adjust the system by simply killing off the most heaviest process. Like an example I would have in the past may have been just that, where I would run a copy of Windows inside VirtualBox. I would have a browser going with like 50 tabs or whatever, and I may have like some other things like some database software, like dbeaver, or even like the actual, what was the other one? Redis Desktop Manager running, and all these things can be pretty RAM intensive if you don't watch out. So I would sometimes run into a situation where I'd consume all my memory and all my swap, and the system would just bog right down and be unresponsive. And if I was lucky, I'd be able to kill off the web browser and get things back and into a functional state, and then recover my web browser and the tabs I wanted to keep active and keep going. But this sort of clears that issue up a bit for you, because now you don't have to kill the entire web browser in a panic. You can just go and kill one child process and restore any tabs that crashed that were of importance, hopefully not lose anything you were working on at the time, and keep going. So if you've enjoyed this, make sure to like and subscribe and click that little bell down below. And if you want to, leave a comment below if you have any, questions, or if you have any feedback for me. I'm more than happy to answer anyone that has any questions about this sort of stuff and try and help as I can. Anyways, take care, and I'll see you next time.